Hello and welcome back to my Applied Data Science channel. For those of you new here, welcome. My name is Ioana and I'm a senior data scientist. In this video, we are going to perform exploratory data analysis, but this time on time series data. So let's jump straight to it. I'm going to post the link from where you can download this dataset in the video's description below. I want to mention this is a real dataset which was not cleaned before, so you can take this opportunity to perform some cleaning yourself. You can also read about the dataset from the dataset's description, but I can also tell you that this data is electricity consumption data, and it was collected by installing some devices on buildings in Portugal. These devices are called smart meters, and they were set up such that they would aggregate the electricity consumption every 15 minutes. So over a 15-minute window, it would sum up the electricity that was used by that building, and it would send it to the database. In order to see exactly how the dataset looks like, we first need to import some packages, NumPy and pandas, and then we will do some data processing with datetime and visualize the data with seaborn and matplotlib. So we are going to import these packages. From the link that I post in the description, you should download the dataset and store it somewhere on your computer. I stored it in a folder called dataset Loureiro dataset, and then you will have a CSV file over there. And by passing this path where you store the dataset to the pandas read CSV command, you can load the data in memory. We are using shape to get an impression of how many rows and columns this CSV file has. So it has around 46,000 rows and 173 columns, and we are also printing the head of the table. So we see over here we have a first column called time. This is the timestamp of each of the records that were sent in the database. And then over here we have energy meter 1, 2, up to 172, which are each one of our devices that were collecting energy consumption data. So the first thing that we need to do when exploring the dataset is make sure that the data types are correct. So to check if the data types are correct, we just call the method dtypes on our data frame directly, and we see over here that all the device columns are float 64, which is correct, but then the time column should be of date time type, but it's of type object, which is actually string in Python. So we will need to cast the correct date type to the column time. How can we do it? By using pandas to datetime and passing in the column that we want to change the data type of. Okay. And now what we will do is actually replace the values in our current column with the new values, and check once again the data types and make sure that the change took place. Okay, so now we can see over here that our column time is of type date time. This is correct. This is exactly what we wanted to do. Next, we are going to print some summary statistics. So we have an intuition of what type of values we have in our data frame. Describe is the method with which we do that. Okay, so now for each one of our columns, we have some summary statistics, such as how many values we have in each of the columns, the average, the standard deviation, minimum and maximum values, and so on and so forth. Okay, so first what I want to do over here is also regarding the time column. I can see over here that I have the starting date and also the ending date of the period when I collected data. Now I see that they are collected at a 15 minutes time interval, and you can see that over here. We start at 12 and then 12:15, 12:30, 12:45 and so on. So what I want to do now is see if in between these two dates, the minimum and the maximum date, I have exactly 46,608 observations or timestamps, because I want to check if I have a full date range or if I have some timestamps that are missing for which I did not collect any data. The easiest way to check this is to use a function that is going to generate exactly the full range of dates. So from pandas I have the date range command, and in here I'll have to put in some parameters, which are the starting date, the end date, and the frequency or the period. So the frequency, I know it's 15 minutes, and then the start and the end date, I just take it from the summary statistics, like from the describe method, from the describe table. I will use these commas, and then the minimum is going to be the start date, and put that in quotes. So now if I print the output, I see that I have the full range of dates at a 15 minutes interval, and the length of this index of this array is 46,608, which matches the count or the number of observations that I have in my data set. So it is correct from the point of view of the length, but then I'll also need to check if I do not have any duplicate timestamps in my column. So how can I do this? First, let me call this object full date range. Okay. So what I can do is compare the full date range with the column in my data frame, which is called time. And then I'm going to use the assert function, because assert is going to check the validity of this equality, and I want all the values to be equal. So assert will output true if all the values in the two arrays are equal, and if nothing happens, it means that the condition passed. So it means that it is true that the content of the two arrays are the same. So I checked then if in between these two dates that I have over here, I have exactly the same number of observations, and also if each one of the timestamp is different. Then another thing that draws my attention is that I have the counts different. So the number of observations for each one of the columns is different. So I want to create a histogram that would give me an intuition of how many observations or measurements each one of my devices has collected. And I know that if my devices were to collect like one data point for each one of the timestamps that I have here, they should have 46,608 measurements. But as I can see in the summary statistics table, that is not true. I even have energy meters or devices that only collected 9,000 observations. So I need to create this histogram and see exactly in how many of the cases do I have like full range measurements. And to do this from this summary statistics, I'm going first to call this summary statistics. So now from this summary statistics, I'll have to extract the values which are on the first row except the count of time. So I'm going to use ilog in order to define exactly that I need the first row and then all the columns from the second one on. This is going to give me the values in the first row for each one of the smart meters, of the devices. So now the idea would be, okay, extract all these values and plot them. Okay, and this is my histogram, and I can see over here that I even have some devices that collected very few points, like 5,000 points or so, and then I also have devices which collected over 40,000 measurements, which is great. So out of the 172 devices, let's say around 90 of them collected almost full range data. Okay, so the next thing that we want to do is check for duplicates. But we already know that we do not have duplicated values because we've checked that the timestamps are different. So we will sum up all the duplicated values and we see over here that the number is 0. So we don't have any duplicated rows, and this is also because of the timestamp, which is different for each one of the rows. Okay. The next thing that we will do is missing value analysis. Okay. In order to perform the missing value analysis, what we will do first is to set the time column as an index for our data frame. So we will overwrite the energy raw data frame and set the index of this data frame to be the column time. Now, if we visually inspect how our data frame looks like, we can see that time has gone from a regular column to an index column, which is exactly what we wanted to do. So what we can do now is to count how many of the cells in our data frame are NAs, because we see over here that we have some NAs also in the first rows. If we use the isNA method, this is going to give us a boolean on the entire data frame. We will have a true where we have an NA and a false where we don't have an NA. If we sum up the NA values, then we are going to get a vector of how many missing values we have on each one of the columns. Because within sum, the default axis is the axis of the columns, which is 0. If we change the axis to be 1, then we are going to have one number for each one of the rows. And each number is going to be the count of missing values for that particular row. So when we perform the missing value analysis, first what we can do is apply sum twice, and then we have the total number of missing values in our data frame. And of course, if we want to get a better intuition, we should express this as a percentage in the total number of cells of our data frame. So we have energy raw, the number of missing values, and then we need to count the total number of cells. Energy raw size is what we are looking for. And we see that 25% of the cells in the data frame are missing values. So this is quite an important number because it means 1/4 of our data is missing. So then here comes the question, what should we do about it? Okay, now that I've shown you how to extract how to count the missing values per column and per row, let's continue with that. We don't get much information from displaying the data in a tabular format. So let's calculate the percentage of missing values per column, percentage of none by device, by dividing these counts to the total number of rows that we have in the data frame, which is nothing else than the length of our data frame. Okay, so now we have percentages and we can better visualize them by plotting a histogram. So let's see now what's the distribution of these percentages. We are using the hist plot from seaborn, where we also specify the number of bins to be, let's say, 20. Okay. So what's interesting is that we have some devices which have over 60% of the data missing, so way over half of the data missing. And these seem to be some outliers. We have this gap in the histogram which indicates outliers. We also have a secondary gap above 80%. Okay, when we have more than 80% of the data missing, for sure, this should give us an intuition that either something was wrong with the device, or maybe the devices were not put in function, were not started at the same time, which is at the beginning of our period, or something happened along the way. So these would be questions that I would take with me and address them to the specialist who has more knowledge with respect to how the data was collected. If we were to discuss about a real-life project, like in a company. But we also have like a lot of data, a lot of devices which don't have significant losses of data or significant number of missing values. Let's, for example, inspect how would this data look like for devices which have almost the entire data or all the data, and devices who are missing a lot of the data. So given that we have this percentage none by device over here, we can sort these values. And by using the ascending parameter, we can ask Python to sort them ascendingly, ascending true. So this is from the lowest value to the highest value. So the lowest value means that we have a small percentage of missing values. So 10% of the values are missing for these energy meters. Now what we can do is simply take, for example, the first 5 of these energy meters and then the last 5 of them and visualize it. First, let's look at the devices which have a lot of missing values. So we see over here the smart device 38, which has collected data but then stopped collecting. And then there are also some other devices which collect data sporadically, like they collect some data and then it seems that some communication is breaking. And then, of course, we have something that we would expect, data throughout the period. And here what I can see is these lines over here, they indicate gaps in the data collection process, but all these gaps happen to be at the same time or for the same period. So then the next question pops to mind. Were there periods of time when all the smart meters were down and did not collect any data? And we can, of course, look for that in the data. Now we've counted the number of missing values by column. So in order to check for days or time slots when we were missing values, we will check for we will count the number of missing values by row. So we'll create an object, none by date, and by using energy raw is NA, we again are going to obtain the entire Boolean true-false data frame, but then we will sum on axis equals 1. So this is going to sum up all the values that are missing for each one of our timestamps, for each one of our rows. So now let's create a plot. I am renaming the values column as NA count by row and resetting the index, and then I'm also calculating all the values as a percentage. So I'm not satisfied with only counting how many of the smart meters were down, but also like what percentage of the smart meters were down. This is what I want to look for. Do I have situations when 100% of the smart meters were down? And here in the first plot, I can see that, okay, sometimes I don't have any smart meter down, but sometimes I have like 25 of them. But then on intervals, on 15 minutes intervals, I can see that sometimes all of my devices are down. Sometimes 100% of my devices are down, and here towards the end of the period, something very awkward happens. Like we have really high fluctuations, and so I want to have a zoomed in image of this last part of the graph, which I plot next to it. And indeed, I see that the fluctuations are very high. And it seems like sometimes all the devices are up and working, and then all of them are down all of a sudden. So I would take this question again to the specialist that I have, also maybe stating my supposition, like were there some blackouts that were very frequent during this time, or how come that were there some updates of the devices that were performed, or how come that we have all these fluctuations in the working of the devices. Okay, so this would be a valid question that I would have. Besides the fact that for some of the series the values are missing and for others not, the shape of the series are different. So we can see over here that we've plotted like 5 series which have values, almost 100% of the values of the measurements, but their shape is very different. So then one other question that I would have, which is like a fast check that I want to perform, is are there some series which are highly correlated to each other? And in order to do this, I can apply a Pearson correlation coefficient on my data frame. Okay, sorry. I'm going to create a new object, correlation matrix, and on my data frame, energy raw, which only contains the columns as devices, I'm going to compute the correlation, the Pearson correlation coefficient. And I can visualize the pairwise correlation between each one of my columns. So energy meter 1 with energy meter 1, of course, is going to have a correlation of 1 because it's exactly the same data, the same vector. But then energy meter 1 with energy meter 2 is going to have a 2% correlation coefficient. And of course, I'll have some other places, some other pairs for which the correlation is going to be negative. The number itself signifies the magnitude or the strength of the correlation, whereas the sign indicates the direction of the correlation, whether the two vectors are evolving in the same direction or in opposite directions. So this table over here is very large, it's incomplete, and it's also not so informative. So what I can do is to create a seaborn heat map by using the heatmap function over here, and this is going to give me a graphical representation of all the correlation coefficients. And here on the legend, I see that the lighter my correlation, the closer to 1 it is, and then the darker shades are in the negative range, with the purple ones signifying no correlation. And already I can see the diagonal line over here, which is the correlation of each one of the devices with itself. And then I have some other lines which are white and which indicate perfect correlation, so a score of 1. So I'll also want to check why that is. So I can, for example, plot some of these cases. For example, I have over here like 87 probably, which is a straight line. I want to see how this data looks like. And this data looks like a straight line. So probably this is 1 meter or one device that I would like to eliminate from my data set, or I would like to ask more questions about. And then there are some others. For example, I see here like 130, maybe 7. So let's check that also. Okay, so this has a spike at a particular date. I would also want to ask about it. So I would put over here all the smart meters that I have questions about, which are weird from this heat map, and I would like, for example, to learn more about or just exclude from the data set if I don't have anyone. Another thing that is very clear from this matrix is that the information repeats itself. So I have this upper triangular matrix and the lower triangular matrix. which has redundant information. First, let's define a new object called IL, and this is going to contain the indices of what's going to be taken into consideration and what not. So the triangular matrix. And we pass in 172 as the dimension of our matrix. Then what we need to do is convert the correlation matrix into a NumPy array. So first we will create a copy of our correlation matrix and convert this matrix to a NumPy array. And we are going to call this, we are going to call it triangular correlation, for example. Yeah. Okay, if we look at what we have now, we have a NumPy array, but now we don't have like any column names or indices, we just have an array. So now if we just pass in the indices to our triangular correlation array and set all these indices to be none, we can look now at our array and see that we have nones in some of the places. Like these places are going to be the lower triangular matrix. So what we can do now is to convert this into a pandas data frame, like to visualize it as before. We pass in the data to be the triangular correlation and we overwrite it. So now triangular correlation will be a data frame, and then the columns are going to be the name of the columns in our correlation matrix, and then the index is going to be the same. So in the correlation matrix we have the index, and that's going to be also our index here. And now if we check the triangular correlation, we see that okay, now the diagonal is none, and then everything that's below the diagonal is also none. And if we want to visualize it, then we can again create a heatmap with seaborn and pass in this new data frame, which is the correlation, but only like the upper triangle of it. Why should we do this? If, for example, we want to extract those pairs which are very highly correlated, when we will iterate over the columns and rows, we will make sure that we don't duplicate the pairs. Let me exemplify exactly what I mean. Okay, so let's extract all those pairs of devices which are highly correlated. So everything that has correlation above 50%, but below 1, so we are not interested in the perfect correlation, or it has also a correlation under minus 0.5, so something that's below 0.5. So we would take the extremes. And then let's print the correlations and the pairs of energy meters. So we will have to go on each row and then each column, and then just extract from the matrix the value of the Pearson correlation coefficient. And we can see over here that we have pairs of devices which are considered to be highly correlated. Let's take one pair from here and plot it to see how two correlated devices look like. Let's take 49 and 32, which have a correlation of 63%. And we can see indeed that the shapes of these two devices, like the energy consumption signal, has similar shape. Next, we are going to try and see if there is any monthly pattern in our data or some weekly pattern, just to get a better intuition of our data set. So we are going to scale the values, and we are going to import standard scaler from scikit-learn preprocessing and just initialize the scaler. So we will have the standard scaler, and we are using fit transform. Okay. And now here we pass in energy raw, which is going to be a NumPy array. Okay. And this will be the data frame which is scaled. Now we will convert this array to a pandas data frame again. Okay. And we will pass in the columns to be the columns of our energy raw. Okay. And this data frame is going to be called energy df. So we are not overwriting energy raw, but creating a new data frame where we know that we are storing the scaled values. And again, the index, I'm going to also say that the index is going to be the index of energy raw, which is the column time. Okay. Okay, so let's print the first 3 rows of our data frame. So now these are the scaled values of our data frame. Okay, so now that we've scaled the values, now we can do some analysis and check if there is any seasonality, if there is any monthly variation that is common to all the smart meters. So now we are going to create some new variables. In energy df, we are going to create a variable month of year. Okay, and this variable is going to contain January, February, March, and so on, but discarding the year, so just the month. Okay, energy df index, and the date time package month name. Okay. Okay, so the idea is I cannot apply this directly on the index, so I'll have to convert the index to a regular column by resetting the index. So energy df is going to be energy df reset index. So now if I want to check the first 2 columns, 2 rows, I can see that I have a new column here, time. So I'm going to use this column in order to extract all of my other time-related values for the columns. So for month of year, I'm going to use the column time and using also the date time package and extract the month name from this particular column. Let's see how this would look like. at the end I have a new column which is called month of year. So now I can see here I have May, June, July, whatever I'll have. Then the problem with this is that if I'm going to want to plot these values, they will be placed in alphabetic order. So what I might want to do is to add in front of the word the number of that month. So here I should have 5 May, because May is the 5th month of the year. And this way I'm going to ensure that all my months are going to be sorted as per the calendar and not alphabetically. So I'll have some continuity in the data. And how should I do that? So first of all, I'll have to zip the month. This is going to output a number, 0 from 1 to 12, 1 for January, 12 for December, and this is going to output the name as in this column over here. So I'm zipping these two values. And then what I'll have to do is, because this object over here is going to output a number, so 3, 4, or so on. And then I'll also have 2-digit numbers, 12, 10, or for October. I need to make sure that all of my numbers are going to contain 2 digits. So here what I'm doing is converting the number into a string, and then if the number contains 1 digit, I'm going to add a 0 in front of it. So if I'll do this, I can see that the object or the values returned are month of year number and then the name. Okay, so I will also create some other columns. For example, I'll do the same for day of the week. I'll have day of the week, the name of the day, Monday, Sunday, but then also the position of that day in the week. And again, I'm going to make sure that this is a 2-digit value, although I only have like 7 days. But just for consistency, I would not have the risk of like mixing 1-digit and 2-digit number there. Okay, and here after creating all these columns, I can see them here at the end of my data frame. Okay, so now that I've done that, I can actually go and perform some aggregations on the data set. First of all, I'm going to check the monthly periodicity of my data, and for that I'm going to create a list of column names, everything that starts with energy, because now I have additional columns like month of year, hour, and so on. So I want to discard all those columns. And to this list, I'm going to append exclusively that column that I'm interested to study right now. So for now, it's going to be month of year. This is going to output the column names that I'm going to work with for this particular investigation, and that's the monthly periodicity. So first of all, I'll have to reindex my data frame such that time is on the such that the time column is an index column. So I'll have energy df that I'm going to overwrite and say set index, and here I'll pass in the name of the column that I want to set as index. Now let's calculate the total monthly consumption. So we are not going to take into consideration any device level. So we don't care about how much energy each one of the devices recorded. We just care which is the average amount of energy that was used per month. How are we going to do that? So our energy raw data frame looks like this right now, and as we can see over here, at the end it contains the other variables that we created, the other columns. So first of all, what we need to do is to only select those columns that are of interest to us, which are the ones defined here in calls. And because we want to calculate the total amount of energy per month, we will get rid of these columns over here by putting them on the rows and then discarding them. So we use the function melt, and the parameter id vars is going to be our month of year column, because this is something that we want to keep. So now we have such a data frame. So if we were to discard this variable column, we would just stick with month of year and the values. So we don't care from which energy meter the consumption came, we just care about calculating the month average. So let's call this object monthly. And then we are going to clean up monthly a little bit by renaming the columns. Okay, so we care about renaming value. This is going to be called average load. Okay. Okay, and then what we need to extract are, as I said, just the two columns that we are interested in, which is month of year and now average load that we've renamed the value column. Okay, so let's call this object monthly. So we overwrite it. And now let's see how it looks like. Okay. It looks like this. What can we do now? Well, we can group by month of year, and by month of year we can calculate average. So that's mean. And as we can see here now, we have the standardized values. This is important to keep in mind and to notice. We have the standardized average load for each month of the year. And why is this important? Because if we've inspected visually the data before, we saw that we have data from 2022 month of May until 2023 month of September. So we have more than 1 year of data, but not 2 full years. So there are some of the months that are going to have double the data just because they are observed twice in our data set. Mainly, this will be May 2022 and 2023, June, July, August 2022 and 2023. We want to calculate the averages just because we want to have more clear understanding of how the monthly behavior looks like. Let's name this object average monthly, and then let's plot it. Okay, so we see over here that all our months are ordered the same as in the calendar, because we took care of it when processing the data. And then we start with January. The energy consumption decreases, hitting a low in April and May. Then in June it starts to increase again, like here, hitting a new peak in July. And September, October are again months with lower energy consumption, after which the energy consumption is going to start growing, hitting the peak in January. Okay, so these are the monthly average load, so how much energy is used on average by all the buildings, with data coming from all the devices, all the smart meters. Another thing that maybe we would like to take into consideration is the standard deviation of these values. So this is something very easy to calculate. We just do exactly the same, but put here standard deviation monthly. Again, we rename the columns, we group by month of the year, and then calculate the standard deviation. And we can actually plot these along the same graph. Because we also care, okay, let's see what's wrong here. STD load not in index, STD load not in index. Okay, it's just because here I overwritten it. Give me a second, I'll just put this monthly to be like that. Okay, and now everything should work just fine. That's what happens when you overwrite things. Okay, so what we can see over here is with green, the standard deviation. The standard deviation is quite high here for the month of July and for the month of August. Maybe it is because of the outliers. Maybe the outliers are those that are pulling the average up for these months. And then, of course, the standard deviation, when you have a distribution which has a lot of observations in the tails, that has outliers, is going to also increase. So, okay, this is something that we should keep in mind and maybe investigate a little bit further. So what are we actually then looking at here? Well, we are looking a little bit deeper into what happens in terms of the distribution of the data by each one of the months that we have in our data frame. So we are plotting box plots over here, and we can actually see very clearly that there are some outliers, both positive or both in the right tail of the distribution and in the left tail of the distribution. But we can see a clear pattern, and we see over here that the months of December, January, February of 2023 record a higher energy consumption, and then we see also that the summer months, May, June, have lower energy consumption. Well, 2022 July has outliers, and also maybe these outliers are the ones that are dragging the distribution a little bit. As we've seen here in the plot, these are the ones that probably cause the higher variation, the higher variation, and consequently the higher standard deviation. We can see here something interesting, that in June 2023, the data seems very consistent. There are few outliers, so I would be curious what happens during this month precisely. We see a similar phenomenon here in November, but in September, but here the answer is clear. Like, we only have a few days of data. If we go back to our summary statistics, we see that in November 2023, we've only recorded the 1st and the 2nd of September. I hope I said September also, with all these months. Okay. So I would be curious to see what happens here. And then if I get rid of some of the outliers, I want to have like a zoom in into what's happening in terms of periodicity and fluctuation. I can see that indeed, like, July exhibits like higher energy consumption, also August. And then we have like a valley and again a peak in winter. So for sure there is some periodicity with respect to the months. Then the question is, do we also have some periodicity with respect to the day of the week? And again, I'm looking at the standardized values. If I were to look at the non-standardized values, because I've done this previously, prior recording the tutorials, I would not see any kind of difference. But once I standardize, I can see actually, okay, again, outliers, but zooming in. On Saturday, we have a higher consumption of energy, whereas on Sunday, we have lower, maybe because people are not doing laundry on Sundays, or who knows. And then again, like, quite constant energy consumption during the week. So this is something that we also want to keep in mind, depending on which is the direction that we want to take this project further. Talking about potential directions, there are at least 3 directions that I could think about. One is related to the downtime of the smart meters that we've observed in the data. It might be of interest for the people maintaining these devices to have a prediction, to have an alert system that could alert them whenever particular devices are at risk of downtime, because we've seen that there are some instabilities in the data. So after clearing the reasons for those, I could propose such a system, a predictive maintenance system. Then another potential direction would be predicting which is the energy consumption for a particular building, or which is the total amount of energy that is consumed in this area where the smart meters are installed, so overall. And then in order to maybe have a better prediction accuracy or be more efficient when performing such predictions, it would be interesting to cluster the smart meters based on different patterns and then just predict at cluster level. So do not develop a model for each one of the smart meters, but rather find groups which are similar to each other, cluster the smart meters in those groups, and then just predict or create one model for each one of these clusters. These would be 3 potential directions. I am not going to spoil the surprise with respect to which of these directions I'm going to follow in the next video. So if you want to receive an update when the video is going to be live, then don't forget to hit the subscribe button. And if you've enjoyed this tutorial and found value in it, please like, share, or comment, just to let me know that I should keep investing time to do such tutorials. I hope to see you next time. Bye bye.